So in the previous lectures, we managed to obtain the market data, and now we want to really use market data to try out certain ideas that we have and see whether they were profitable in the past. To do that, we want to create an alpha library and implement the strategy logic using the alpha library. But before we go into any strategy implementation at all, we want our library code to be a reusable and flexible system. Because if not, if we cannot use our alpha library into implementing different strategies, then we are going to have to write a lot of repeated code every time we have an idea. So ideally, our library is powerful and flexible enough that it does not depend on the strategy. And when we have a strategy, we want to write as minimal code as possible. So that is the idea of programming in general, is that we really want things to be as abstracted away as possible. You don't want to have to deal with the details of the internal implementation details where it is not critical. So for example, if you have an alpha strategy, the critical detail is how you generate the alpha signals. You're not really interested in how the PNL is computed, because it doesn't matter if you're trading a momentum strategy or a mean reversion strategy. Most of the time, the PNL calculation is going to be the same. So you don't want to be repeating this same logic pieces in different parts of the code or in different parts of the application. To do that, our objective is to program a utility alpha blueprint so that we can use this class in implementing our strategy logic. So we're just going to see exactly how that works. For now, it can be a bit abstract, so let's just go ahead into our utility file and implement a very generic alpha class, right? So this is not associated with any strategy. We're just saying, okay, any alpha is going to take on this form. So what are we going to pass into this alpha? So it doesn't matter whether we are working with a momentum strategy or statistical arbitrage or anything like that. We always want to take in some data. We want to take in some information about when we want to start and end the backtesting date. So starting from here, let's instantiate this. Let's assign the variables to the object. Now, if you don't know by now what a object or class is in programming, well, that is completely out of the scope of our lecture series, and it's very easy to pick up. You should watch a video, and it should take you less than 10 minutes to understand exactly what a class or object instances mean in programming languages. So we're not going to go into such low-level detail, and we're going to assume you already know what the syntax here means. So we want our alpha class to take in certain data and certain settings about when and how long we want the backtest to be. And of course, the data frames should contain the relevant period's historical data. And we want to be able to run a simulation, say this, and this would allow us to do something like alpha, and then pass in the parameters, and we can do something like alpha.run simulation, right? So you'll be able to do this particular function call. Actually, let's do that right away, so we can do it from here. So from utils, import alpha. Let's make that a little bit smaller. We can do alpha equals to alpha, ends equals to tickers, dfs equals to ticker dfs, start equals to period start, and equals to period end. And we can basically do something like this, and we are running the backtest over here. So this is, this shouldn't be problematic to anybody. It's quite a simple piece of code. So, of course, we now want to implement the logic for the backtest. And that is the more interesting part of this lecture. Note that when we retrieve the historical data inside this ticker dfs, naturally, the date inside the datetime column inside the index of the data frames are not going to be equal, because some stocks have been around for longer than the other. So of course, Tesla is going to be traded from some year to another, but like Apple is going to have been around for longer, and we really want to standardize the date range for which they are traded, because some stocks will stop trading and then they'll start again. because the date ranges are very different for each individual ticker, we want to standardize the dates for which they are traded. So this is the period of the backtest we want to run. So let's just create a date time. Let's just create a date range. So start. So let's import pandas here, and what this will do is pretty much create a what am I doing there? Oops. Okay. What this will do is basically create a date range from this date to today's date. So we have a good date range, and this is the datetime index. And this is well standardized across every single asset, and we will align and arrange the data according to this datetime index. We want to build up a data frame that contains information about our portfolio. So let's say we do portfolio df equals to portfolio settings. Okay, so let's implement this. So init portfolio settings, trade range. Okay. So what do we want to return? Let's create an empty data frame first with the index as our datetime index, right? And let's say we want to have the integer as the index and a datetime as the column. So okay, we're going to do rename. Then you can already see what this thing will be. So let's just take a look at what this will be. This is datetime index. We'll pass the date range into. Oh, okay. We need to put this here because this is a mistake. Let's see what we got here. Yep, so we got a data frame. So this print up portfolio will show something like this. And this is the data frame that we're going to slowly build up during the entire simulation. So let's try something like set our initial capital to 10,000. And then we return this portfolio data frame. And this is the data frame that we will keep building up throughout our simulation. Okay, and then we want to basically go through each of these rows and populate certain information about our strategy. So the date is going to be log I datetime, and this is going to print the date. We're just going to get this, and we're going to iterate through each of the dates. Now, if you're not working on the first date anymore, then we want to do some things like, okay, what do you want to do here? We want to compute PNL, etc, and update our trading capital. Otherwise, if it's not the first date, otherwise for any other date, we basically just want to compute some alpha scores, right? So we want to have some forecast for each and every. We want to have a forecast for each and every instrument inside our trading universe, right? And then we want to. So here we will compute alpha signals, followed by compute positions and other information. And this will just basically be the general structure of our entire backtest in a very, very high level. This is the skeleton of what they are going to implement. Okay, so far, nothing interesting. Before we go into this backtest, we're going to, okay, before we go into the backtest, as we said before, it's not true that at every point in time here that every single instrument was alive. Some instruments only started trading in 2015 or 2020, for example. And in these scenarios, well, we want to be able to differentiate between the stocks that were basically alive at the point and those that are not eligible for trading. And we call that our trading universe on the run. So we'll do this computation before we go into this for loop. Right? So let's say we want to compute some meta information, right? So this straight range, and we'll pass in our data range. So again, we'll implement this. So compute meta information, straight range equals to yourself and pass. Right. Here, we will compute some useful statistics. So for instrument and self-ins, so this we already instantiated here. So let's create an empty data frame with the index as trade range, right? So let's check two things. Okay, let's print out the data frame that we just created, and let's print out the data frame that contains our historical data. So let's see that over here. So our data frame that we just created is an empty data frame, and this is daily indices, and the indexes are just daily indices, right? So this is very regular. On the other hand, you can see our data frame, right? Sometimes there's data, then there are trading holidays and weekends, and then there's some data, and then it's not regular. So what we want to do is to basically have consistent aligning for each asset. If you go down the line, you'll see that sometimes the data doesn't exactly start from 2009. So this starts from here, but you see that, okay, some of the other assets start later. And we want to make sure that we have a consistent structure for the data frame, because this will make it easier to manipulate, right? So we're going to do this by using what is known as a join method, right? So this is, well, you can check the specifics inside the documentation. And for those of you who understand SQL, this will be nothing new. But what this method does is we're going to take the index of this, right? And we're going to fill whatever, we're going to match the indices. So in order to explain this, let me just go to my iPad, right? So let's go to my iPad. So you'll see that the data frame that we had an index that is, say, quite regular. So for example, we're talking August 1st, August 2, and every day there is data. So August 3 and August 28, August 29. On the other hand, our market data was a little bit irregular. So sometimes we would have, say, August 1, and maybe we skip August 2, and then we go to August 3, and then August 28, and then August. And okay, so suppose that there was missing data here. So here there's missing data, and here there's missing data. When we do df.join, what happens is we do df.join. So this is we call this the left data frame, and here I believe it was self.dfs.inst, right? So this is the right data frame, right? So we will look for the matching indices and fill in our data. So the rest of this will just be, inapplicable. But now we would have a full data frame that has the original data. It has the original data with the missing columns specified as not applicable. So we will see what this does. Let's try to run that again. So now we will see that the second data frame, which is over here, has missing columns, but we will have the entries completed where there was available data. So, and then what we're going to do is we're going to fill the data forward first, and then we're going to backfill the data. Right. So DNA. Now again, what this is going to do is quite simple, really. So if you see this, it's going to take to fill NA means, okay, suppose we have a set of data, and this is like A, B, C. Forward fill refers to A. These are, imagine these are missing, right? And then it's going to fill the data, right? And then the backward fill is going to then push this behind and go like that. So we're going to fill in the missing data like this, and then we'll fill in the missing data like that. And this will now ensure that our data frame has no empty 20 rows. So that's pretty good. So, and using this, as we want to compute return statistics. Later we can use this to compute our P&L, so this will be useful. Right, so set the dfs and rows dot shift. Okay, so what this dot shift does is it basically just moves the entire data frame one row down. So it is taking today's prices divided by yesterday's prices and then subtracting, because this will be the gross return and then this will be the net return. So if like today's price is 110 and yesterday's price is 100, then this will just give us 1.1 minus 1, which is 0.1, indicating we have a return of 10%. This is not very complicated. The next thing we're going to do is check if the instrument is being treated. Remember, we already filled all of the data, right? So what this means is that if we forward fill everything and backward fill everything, even though, let's say you started trading in 2013, if we backfill the data, there is going to be a number for each of the rows, even if the instrument did not trade at the time. And in order to be able to detect this fact that they were not trading at the time, or maybe they were halted or not actively being traded, we're going to create a series which checks if today's prices are the same as yesterday's prices. So if there is a difference in the prices between today and yesterday, let me say that there is a new sample. So this is going to look something like this, right? So that means today's prices are different from yesterday's prices. And in this case, because we backfill, there is no entry, and the prices here are all the same. So this is what we're saying. And we're going to assume that for a stock to be considered as eligible for trading, we want there to have been at least one new sample in the last 5 entries. Okay, so this is going to take in so let's import numpy, SMP. So what this does is basically, okay, let's take a look at this function and see what it does. So I want to explain what this function does. So again, let's go to our iPad to explain exactly what that statement does. So remember, we have a list of closing prices. So for example, this is first closing price, second closing price, third closing price, and so on, right? And then we check to see if this price is the same as this, the same as this, the same as this, so on and so forth. So for example, we'll have false, true, 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 false, true, true. And we can keep going. So suppose we have false, 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 true. Okay, so let's suppose this is our sample variable. In order to see whether it's eligible, we're going to do a rolling operation. So what a rolling operation is it will group eligible equal. I think we did something like sample dot rolling 5, and then we'll dot apply. So this func was basically we applied some function to our rolling data, right? So we do something like func x. So this x is just this x, and what will happen is it will just create this sliding rows like this. This will be the first increment, then this will be the second, then this will be the third, and we'll keep creating. We'll keep applying this function to x1, then x2, and x3, and so on. And we'll create a new data frame. We'll create a new kind of series. And what it does is we'll group these, and we did something like int mp dot any x, right? Something like that. So what this does is see if any of this is true. So, well, we have at least one true, so this would, okay. We have 3 true, which is at least one true, so this would be true. Then we will have the next row. So again, we have at least one true, so this will be true, and we will have mostly true until we arrive at this. Until here, it will be at least one true, so this will also be true. But then when we come to this, we'll realize that, okay, all of them are false, so this will be false. So this is our new pattern series, and then this will also be, the next row will also be false, and then we'll come across a true statement, and this will be true. So this is the resulting object from the pandas series. And then we did this as int. So int true basically will give us 1, and int false will give us 0. So this we're going to map to one something like a column of 1 0 0 1 1 1 1 1 1, and then we did dot fill na to 0. So we're just going to set the remainder of this to 0. So that is basically what we did in the operation. So this is our operation, and we're going to say, okay, self.dx, if it's eligible, we will treat this as a integer data frame. And let's say we want some other conditions, right? So here we can specify any other conditions we want in order to determine that our trading universe. And we can really say anything, that any behavior that we want. So for example, if we want to only trade stocks that have closing prices above 100, or if their average daily dollar trading volume is a certain amount, we can do the filtering over here. We're just going to do a very simple one and say that we want the closing prices to be non-zero. Okay, so this should really be every, or almost every stock. Sometimes prices can be negative, but that is very, very rare. So anyway, this is what we're going to have. Let's see if everything runs fine. So let's try something like this and see how that looks like. So that's nice. Now we know at this point we will treat the stock as not eligible for trading. And here, these are all eligible for trading. It's possible somewhere in the middle it halted trading and we remove it from our universe. Okay. Now here would be a nice place to define our trading universe, right? So eligible is equals to int for int int if self.dx int .block date eligible. Okay. So this is our trading universe, and then int for int not eligible. So for our entire trading universe, this is the trading universe for that particular day, and then this is the not the invalid instruments for that day. Since you're working with with random strategies, for demonstration purposes, let's just create random signals. Okay, so for ints and eligibles, we want to create we want to assign an alpha score. So let's say we assign a score from 0 to 1. Okay, so let's take a look at what this does. Take a look at what this does. We're working with 500 different stocks, so let's go to our main file. Let's just test for, say, 20 different stocks. So table is equals to that is so that we can just make our demonstrations quicker. So let's try that. And we're running the backtest. Okay, so our first alpha score is, well, it's an empty dictionary because there are no eligible stocks, but I mean, we can keep going and soon we'll start receiving forecasts. And let this be alpha signals. So in practice, this alpha scores would not be this random number. These will be the numbers that you assign them to be. But let's just assume that for now the signals are random. Okay, and we can do something like maybe we want to sort these numbers. So KB. Okay, so what this does is very simple. It's just going to sort this dictionary by the value of these key pairs, and it's going to use the pair basically. It's basically going to use this value. And so here is random, but we're going to assume that the higher the score, the more we want to trade it, and the lower the score, the more we want to short it. So assume you're going to have a long short portfolio, right? So we're going to go long the top 25% of this alpha scores, and then we're going to short the bottom 25% of this alpha scores. So what can we do here? Okay, so alpha scores dot keys, and we will take the highest 25%. So this is what it does, and the short component will basically be, we'll take the first 25%. So that's going to be here. Okay, so let's just make it very clear. To make it very clear, we will just show it to you. Okay, so let's see how that works. So let's try it again. Okay, so we've skipped the first few. Okay, so here we have a sorted dictionary because we already sorted it here. So it's going to be the lowest, and this is going to be the highest, as you can see. The numbers are increasing. Then we're going to take the first 25%, but it's non-inclusive. So we're going to look at the first 4 stocks. So it's going to take AFL, ALKA, and ADP as the short stocks, and then it's going to go long this last 4 stocks. So far, okay, not too complicated, but also not so interesting because the signals are just random and it doesn't do much. And let's say, with this we can already compute. We already have the alpha signals. The signals are either they're inside this long or short basket, and we can already start trading this thing. So we want to allocate portfolio weights. So if they were non-eligibles, then we would basically assign their weight to 0, right? So these are not interesting for trading. So the portfolio weight and the total number of contract allocations would be 0. This is yep. And then otherwise, these are the eligible stocks. And our forecast is 1. It ends in alpha long. Otherwise, negative 1 that ends in alpha short. Otherwise, it's 0. So if it's in the long basket, then we will go long. Otherwise, if it's in the short basket, it will go short. Otherwise, we'll take 0. Our dollar allocation will be okay. With trading, we have a total amount of this amount of capital, right? And then we want to divide it equally among the long and short basket. So this is an equal parity dollar allocation. Then the position sizing we would take is basically the direction of the forecast multiplied by the dollar size allocated divided by the size or the price of the instrument. So this is quite easy to understand. So this is the amount of dollars that we are given to do the betting. This is the direction of the betting, and this is the minimal size of the bet. So we can assume we can have fractional contracts. So this is going to be a floating point. We can start building up the data frame here also. So we'll take instrument plus position. Then we can put derived units equals to position. We also want to keep track of the total nominal value of our portfolio. So nominal total, that's equals to the absolute value of the position multiplied by the closing price. So this is what we're going for. This is the absolute value of the position sizing in terms of dollars, right? Okay, so constraint ineligibles is equals to, we already assigned this here. The nominal value of this instrument would be the number of units multiplied by the close. So this one is it's not an absolute value because we can have plus or negative sizing. We can be betting a positive number of units or a negative number of units. So this nominal exposure is either positive or negative depending on whether we short or not. And our portfolio weighting would then be the nominal value of the instrument divided by the total nominal value of the portfolio. And we can then assign the weights, and then we can give some more information to that. So nominal value of that would be the total value of the total nominal exposure, probability of the block, by the leverage of our portfolio with the total nominal exposure divided by the amount of capital that we have. So these are all very simple to understand, and this is what we have. Okay, so that's fairly interesting, right? All we need to do now is to compute the P&L for our portfolio, right? Because otherwise, we already have just a single computation. Then we compute the portfolio weight, compute the total exposure, and all we're left with is to compute how much money we make or lose in a day. So we'll just do that right now. There's no point holding back. So let's just do the previous step will be portfolio of the block minus 1. Let's put that here. And let's try to compute the P&L. So get P&L stats, date, previous date, portfolio, ints. We're just thinking about what information we'll need. So we'll take in what is the date, what is the portfolio, data frame, so instruments for trading, and some other information. Okay, so we'll see why we need this variables inside later. So let's do this up here. So we're going to do def get P&L stats. Now we need to implement this thing. Okay, so date previous portfolio is what is IDX NDS. So now we want to implement this function, right? So how do we do that? Okay, we want to build up the P&L. So okay, P&L is equal to 0. The nominal return is equal to 0. For each of the instruments, let's look at the. So this is already in the next day. So we want to see what is the purchase in the previous day. So we'll take portfolio DF, block, IDX minus 1 units. So this is the number of units in the previous day. So this is the instrument. Now, if there are non-zero number of instruments, then we want to compute the P&L. So let's find the price difference, right? So instrument, block, date, close, minus the previous date. But this is a change in price. It's just previous. This is a change in price. So the P&L from this position would just be the change in price multiplied by units. So the change in price is negative and we're short, then our P&L will be positive. So if the sign of the change in price and our position is different, then that would be a loss. So okay. So P&L would just be the sum of all of this individual P&Ls. And our nominal portfolio return would be our portfolio allocation to it. Here, multiplied by return of that instrument. So this we already have because we did that over here inside the computation of the meta information. So okay, let's drag it over here. So let's take a look at the entire capital return would be the nominal return multiplied by the previous stage leverage. So this will be the return on the portfolio. This is the return on the nominal exposure of the portfolio, right? And this is the return on just the portfolio because we can have more leverage. And of course, we want to update the amount of capital that we have. So we'll take the previous stage capital plus our P&L, and then we can record the P&L here also. So this will be P&L, portfolio DF, unlock, IDX, nominal return. So this is just, we're building up the data frame to have more information so that later we can inspect it. Okay, let's return the P&L and the capital return. Okay, so this will have the P&L, capital return, and let's see if, I think everything should work now, so let's see if that works. just going to see if each of these rows have information that we want. So let's try this. So all we have created is a very generic alpha that computes the PNL and everything. But in this case, we don't have a legitimate alpha signal creating component. But we use random signals, and we're trading off the random signals. And this will be our data frame. So each day we will compute some information. Okay. So there's an error here inside here. Okay. Day previous one. Okay, so that would be daytime instead of date. So fail here. Let's try that again. Okay, so we're creating random signals, and we're allocating profit weights, and then we're computing the number of units, and we're also updating PNL. So everything here is going good. Also, you should know that the leverage is always fixed to 1, and this is intentional because we have basically designed it to allocate the entire portfolio, right? So this is the capital, and we're saying, okay, divide the position equally into each of the positions that we're opening. So the nominal exposure should be exactly equal to the amount of capital that we have. We're betting 100% of our portfolio in every step of the way. And we can keep doing this. Let's see how that turns out. If I mod 100 equals 0, so every 100 days we want to print out the status of our portfolio, and we want to give back the portfolio to the caller. So here we can do portfolio df. So this has been a long lecture, but this is the core skeleton of our backtest logic. So we will be extending from this vanilla module. So 3.8 pi. So you should really spend some time understanding the entire structure of this, because everything else will build from this basic logic. It's just 100 lines of code, so it's not a lot, but it's doing quite a bit of things here, right? It's building up a data frame, and there is a signal generation component, and then there's also a PNL computation, and then there's some pre-computation of information, and things like that. So you'll see how to extend this and build a legitimate backtesting module as we go into the future lectures. So we can see our portfolio. Okay, as you can see, our portfolio didn't perform very well. We lost about $2,000 during the entire backtest. Oh well, it's functional, and all we have to do is now do this slightly better in terms of the signal generation component. And in the future lectures, you'll see exactly how that is done. So congratulations in finishing this long lecture, and we'll see you in the next class.